All right, and here's section 6.4, multiplicative inverses and matrix equations with me, Mr. Hain. Glad that you guys are back. We talked about matrices the last time, and now we want to know what the heck is the inverse of a matrix. All right, so that's a big question, and really I'm going to show it with some patterns. Inverse of a matrix means that when you multiply a matrix and its inverse, your product will look like this in a 2 by 2, or like this in a 3 by 3. The takeaway here is that the product will always be a diagonal row of ones with every other spot as a 0. That has a deeper implication. Notice it's a 2 by 2 and a 3 by 3, which would mean the next size up would be a 4 by 4. So all of these inverses only occur with square matrices. Kaboom. All right, so first question is the first matrix here the inverse of this matrix here? Now remember, by definition, it means the product of these two matrices would equal this ones and zeros matrix style of diagonal ones and all the other numbers being zeros. So let's multiply them. Throw them in your calculator, see what you get. And if you got this matrix, you're doing it the right way. And yes, 1, -1, -1, and 2 is the inverse of this matrix. All right. So you guys might see a pattern, yeah, it is the inverse, and here's the formula for the inverse of a 2 by 2. So I'm going to give you a matrix. It's going to look like alphabet soup for 3 seconds, and you're going to have to forgive me. So given A, B, C, and D in this style, in this matrix, a 2 by 2, and again, this formula only works for a 2 by 2, the inverse of matrix A, we're going to call this matrix A, is a 1 over this fraction. So I have A times D minus B times C. Order is important and subtraction is also important. So again, A times D and B times C, kind of like in an X pattern, and that gives us our fraction for scalar multiplication. Inside of the matrix, you'll notice the 2 by 2, we have A and D switched places, and B and C also changed signs. Okay, very important. A and D switched places, B and C change signs. Okay, you're going to have to memorize this formula. So let's memorize that formula, put it to memory, pause the video, do whatever you need to do, but that formula, so important, definitely going to have to know it. So I'm going to give you matrix A, which is 3, -2, -1, 1. I'm going to use the inverse formula. So to find the inverse of A, I plug in those numbers. AD is 3 times 1, so we have 3 times 1 here. Minus, which is this minus sign, it'll always be there. And then B times C. Kaboom, here we go. The signs have changed. I'm multiplying them together and kapow. Oh, I'm sorry, not the signs have changed. This is from the original equation. I have B and C. And now I switched A and D, so you see 1 and 3 switched places. And then the signs of B and C also changed, so you see I have a +2 and a +1. All right, so let's start by simplifying this fraction. All right, 3 times 1 is 3, -2 times -1 is 2. Oh man, this is awesome. That fraction turns into a 1. I can scalar multiply these without a problem at all. And of course it is 1, 2, 1, 3. Kaboom. All right, why would we have inverses? And after we see this slide, really all I want you to memorize is the formula. If I asked you to find the inverse of a 2 by 2 on a test or quiz, if you're taking this as a course, but really, we use the inverses of matrices to solve matrix equations. So before, for example, we've got this gigantic 3-variable system of equations. This is foreshadowing to the next section. I can actually put this into 3 matrices. So the first matrix here, this 3 by 3, actually all of those values come directly from each equation. So the coefficient of x is 1, the coefficient of y is -1, and the coefficient of z is +1. And you see that's where I get my first line. And also the second line, 0, -2, and 1, comes directly from the second equation. Since I have no x, the coefficient has to be 0 to make that x not be there. And you see the -2 and the +1. Of course, here the z is not there in the third equation, so that's why I have a 0. Now we multiply that times the second matrix, which is just the variable matrix. So this is the coefficient matrix times the variable matrix, x, y, and z. and that equals the answer or the constant matrix, which is 2, 2, I'm 2, 2, and 1/2, which comes from the constants, or what each of those equations is equal to. Now you're just like, why oh why would I ever do this? Here's why. I can plug this in by naming matrix A and matrix B, and the unknown matrix, matrix X. That's just A times X is equal to B. Now, you want to divide the A to each side, but recall that having dividing by A is the same as saying multiplying by 1 over A. And 1 over A is actually just the inverse of matrix A. You can do that on your calculator. Your calculator will do that for you. Boom. If you multiply these together on your calculator, you get 1/2, negative 1/2, and 1. That hardly took us any time at all. Those are the variables x, y, and z. My systems of equations are solved. That's x, y, and z. Many of you might have experienced solving 3 variable equations in math classes where you did it by elimination and longhand, and it took you 1.5 pages of work. Never do that again. If you've got a graphing calculator, kaboom. Use inverses and matrix equations to solve for x, y, and z. We're going to put this to great use. It's your turn. Let's see if you can write down this matrix and the coefficient matrix, the variable matrix, and the constant matrix. Go ahead and pause your video. And now that you're back, I'm sure that you got something that looked like this. Excellent. Just remember that those zeros come when there is no value for that, or that variable does not appear in our set of equations. Using what we know, A times X is equal to B. Of course, those are all matrices. We use the same exact equation. Let our calculator do the work. And yes, 4, negative 2, 1. And those are our values for x, y, and z, which are 4, negative 2, and 1. Man, we did some good work. And so let's take this to another level. If you have seen the movie U-571 with Matthew McConaughey, you'll recall that that movie centered around a submarine captain's mission to recover the Enigma decoding machine from World War II. True story. It's in your textbook. England employed mathematicians, physicists, chess players, people that were just good at solving logic puzzles to try to crack the code. And if you saw other movies, you'll see that they created a giant machine to eventually crack that code. What wasn't revealed in the movies, because it was deep, deep math, was those codes were based on matrices. Oh, man. So if we know a coding matrix, we can code a message, and we can code a message and have a coded message come out. Okay, that was a lot of coded messages. But here you see, we've got a coding matrix. Here we go. Negative 2, negative 3, 3, and 4. We'll call that matrix A. I have a coded message. Now, we're going to use the simplest code that you ever used when you were a kid, when you first discovered and you thought, hey, numbers and letters, alphabet, 26 letters. A is 1, B is 2, C is 3, D is 4, and so on. But if you received this coded message, what the heck is that 4-letter word? I have no idea. But you can know that if we actually took the coding matrix and we multiplied it by the inverse of the coding matrix, we'd end up with this. So I take the inverse of the coding matrix and I multiply it times this coded message, and it will give me this result: 13, 1, 20, and 8. Using our knowledge of the English alphabet, we will find that those letters correspond to the word math. Yes. Okay, so it's your turn. Here you have a coding matrix, a different coding matrix, and another coded message. You want to find out what word I encoded. Remember, you're going to take the inverse of this coding matrix, and multiply it times the coded message. Go ahead and pause your video, put those in your calculator, and see what comes out as 4 numbers in your 2x2 matrix. If you got 8, 1, 17, 4, I'm going to give you a chance. Go ahead and find out what those letters are. And of course, you know what? It wasn't hard. It wasn't hard at all. I love these guys. It's just a cool way to put together inverse matrices and to code messages. Don't tell future teachers and friends that this is who taught you. how to encode messages. Hint, use 0 for space. That brings us actually to the end of multiplicative inverses and matrix equations, and we're going to launch directly into systems of equations in 3 variables because it dovetails directly into how we solved matrix equations. So we're going to abuse matrices to solve the hard stuff. I'm just gonna throw it out there. So I have a system of equations in 3 variables. I want to show that these are the answers, or that's x, y, and z. Now, in the past, what you would have done is substituted all of those values in and then multiplied and added and multiplied and added and multiplied and subtracted. No, go ahead and put those into your matrix. Go ahead and take that matrix, multiply the inverse of A times B, kaboom, you get those numbers. And those are the numbers that we have here. So we just showed through matrix operations and solving matrix equations that -1, 2, and -2 are indeed the values of x, y, and z. We have satisfied the question without substitution, multiplication, addition, and subtraction. Matrices. Super powerful. That means we can use matrices to solve a 3x3 variable system of equations. Now I'm just getting a little bit harder. Go ahead and pause the video for checkpoint 2 and see if you can solve this on your own using what you found out in section 6.4. If you got this set up, you're on the way. And if you have this as your answer, that's correct. But remember, it is an ordered triplet. So I'm looking for x, y, z, which of course is -1, 2, -3. Awesome. We just solved checkpoint 2 probably in the shorter amount of time than it took for you to watch me just walk through this slide with you. This is some powerful, powerful stuff. And how can I make it harder? By not much. We're actually going to find quadratic equations from points. So this is super cool. These 3 points actually lie on a quadratic equation. All right. So we're going to find that quadratic equation, y equals ax squared plus bx plus c. So we're looking for the coefficients a, b, and c. We have x and y in each of these. So for the first point, -2, 7, I already know what x is. X is -2. And I already know what y is. Y is 7. All right, so I plug that into the equation. And when I plug it into the equation, I have 7 is equal to a times x squared, which is -2. B times x, which is -2, and c. I multiply and square these out, and of course I have 4a minus 2b plus c is equal to 7. And I just put that equal to 7 to the other side of the equation to make it easier to look at, kind of like what we're used to. So let's do the same thing with these other 2 points, 1, -2 and 2, 3. If you would like, take a moment and pause the video and see if you can plug this in to our quadratic equation. If this is what you got, and it's simplified to a plus b plus c is equal to -2, you are correct. Yes, which takes us to the last one, which is 2, 3. Plugging it into the quadratic equation there, we find this and multiply. Move that 3 to the other side, kaboom. This gives us 1, 2, 3 different equations. Of course, all of these equations come directly from plugging in those points into our quadratic formula. This gives us a system of equations in 3 variables. Ladies and gentlemen, abuse matrices and matrix equations. Put that into your calculator. You can tell me what a, b, and c is. And yes, a is 2, b is -1, and c is 3. That is not our answer. Our answer goes into the quadratic form because that is what the question wants us to find. Find the quadratic function. We just substitute in the values of a, b, and c. We have our quadratic function that when it is graphed shows us these points. Super powerful. Let's go ahead and give you a chance to do these on your own. Here's your turn. Go ahead and pause the video. I'm going to take an extended break, which will be time traveling for me, I'm sure. Use these 3 points and use the same method that we saw in the previous slide to see if you can solve for the quadratic function y equals ax squared plus bx plus c whose graph passes through the points given. Man, and if you're back, you'll see that we got these equations from these 3 points by plugging them in to our quadratic equation. And once I have these three equations, of course, I use my calculator, and yes, I got 3, negative 12, 13. That means my quadratic equation is y is equal to 3x squared minus 12x plus 13. Ladies and gentlemen, that's systems of equations in 3 variables by abusing matrix operations and equations. I hope you enjoyed this. There's a part of you, especially a high school part of you, if you took Algebra 2, that should be upset that your high school teachers did not show you how to solve systems of equations in 3 variables using matrices. You're welcome. And be sure to use these. And that was both 6.4 matrix equations and their operations, and 5.2 systems of equations in 3 variables. And I'll see you next time for the next video.